So the project on tomorrow is going to start out trying to prove Newton right or wrong by making photographs that would allow you to put points in a graph that kind of sort of match what Newton did or didn't, that do or don't. But how do we generate the velocities that then you're going to plug into the graph? I have talking about scale. I have a number of these. You can see them there. The scales. They're rods marked off in inches and feet. And the idea here is that there's some mark on there which you might call 0. And then there's the other, what is markers here? What do we have? 1, 2, 3, 4, 5, 6, 7. Maybe you can only fit in 6 feet. I don't remember. To streamline things, to make sort of life easy, the idea would be to take a camera and put it at the same level as 0. Okay. And then, you'll be provided with highly reflective ball bearings, and one of you would take it here and drop it. And the other person tells the camera, make a picture. And then you do it from 2 feet, and then 3 feet, and 4 feet, and so on. The question is, where does high-speed photography come into this? It comes into the fact that you're going to experience, or the idea is, that you would experience many of the things that are associated with high-speed photography. Primary among them is, well, I won't give it away exactly, so I'll ESP again. I'm thinking, it's not in there, okay. Is making sure that the event happens within the frame of your camera. You're looking at something out here. If it happens before, it's no good. If it happens after, it's no good. The data is no good, of course, because you don't have it. The other thing that could happen is that you have data that looks like this. And you might have experienced that last week when you did the moving light thing, you pan. And if the trace ends up outside of your frame, well, you don't know where time started. Or you don't know where it ended, because you could have a trace like that. That's no good. You want to see the whole thing, like that. And in the best of all worlds, you'd like that blur to be centered right there. That's not going to happen. It's not, well, I shouldn't say. The likelihood of that happening is extremely small. Maybe if you drop from 1 foot, maybe. But once you start dropping from 3 or higher, chances of catching it as it crosses that 0 mark are going to be pretty slim. That's my prediction. You can prove me wrong. But never mind. Because we can make adjustments, as you'll see. From a data gathering point of view, to make sure, the term that I was thinking about earlier was synchronization. Synchronization has to do with, well, make that mark show up right in the middle there. Now the other thing is, you'd like that to be small, but not so small that the speed changes a lot from top to bottom. So in order to make sure that the speed doesn't change much, so that the average speed would be equal to or closely the same as the absolute speed, you want to make this as small as possible, right? You want to make the blur as small as you can. However, making the blur small then eventually has another problem associated with it. What might it be? Figuring out how long it is. You know, it's like measuring an inch with a foot. Mark? I don't know. Or measuring millimeters with an inch ruler. So the compromise is you want a large trace so that it's easy to measure, but not so large that it's very different in terms of speed at the top and at the bottom, because then the average speed doesn't equal or doesn't equate closely to the absolute speed at the midpoint. So we might say, well, the length of the blur that we get for that moving object is going to be dependent on what?
Shutter speed?
Yeah, absolutely. So suppose that that you take a look at a field, okay, out here. And let's see, actually, let's do it this way. Like that. So this would roughly be equal to a foot, right? So we fill a frame 1 foot. And from a 1 foot distance, now this is exaggerating a little bit. From 1 foot distance over here, the ball is already traveling 8 feet per second, right? That's what Newton said. 8 feet per second. Let's assume that that's the average rate at which it goes, or the absolute rate from top to bottom. All the time, it's 8 feet per second. How much time will it take it to go that 1 foot distance?
1/8 of a second.
1/8 of a second. So, and you say, oh, that's because now I have as big a blur as my frame. That's easy to measure, right? However, how much synchronization time do you have? None. Exactly, because the blur is just as long as the frame. So you make a little error in timing, and the data is no good. So you say, oh, well, okay, I want to improve my chances of getting a shot. You say, oh, what would you do? Use a shorter exposure time, so maybe you would say, okay, I'll use a 15th, okay? So you have 1/15 for the blur. And how much synchronization time do you have? 1/15, because it takes an eighth. This is sync time. This is blur, right? So now the blur would be about half the size of your frame. And so your slop is a 15th of a second. So this is essentially how it goes. If you start to use a shorter exposure time, obviously they get a little shorter. But see, this was just at 8 feet a second. When you start to go 20 feet a second, well, now the situation changes a little bit, right? Because if we do that 1 foot in a 20th of a second, no, you don't want that. So you go to a 50th, let's say, and that gives you half of it. But you still have only a 20th to catch it. So you want to say, well, okay, I'll use an even shorter exposure time, so my blur is less, but now I have more time to sync, right? So it's a matter, again, of compromise. Choosing a time which kind of feels good. Now, one other way of dealing with sync time is not to cut the exposure time, but to move the camera back, or use a shorter focal length lens, right? So now we take a look at a bigger field. It takes it longer to pass, but now the mark itself becomes, again, harder to measure because it's going to be half the size. So it's, again, a matter of this gut feeling thing. Well, how much do I want to get? Now, because this is not a life and death situation, it's not a one-shot deal. Okay? You have the luxury the digital camera, making a shot, and say, well, you know, I'm pushing it as far as sync because I can't get it. All right, so I'll use a shorter exposure time, or I'll move the camera back or something. So you make an adjustment on the fly. Right? But if your life depended on it, well, then you couldn't do that. You know? And that's where having some idea of how things work, that's what it's used for. I'm not sure, I think I mentioned this. Did I mention something about doing a seminar for high-speed photographers in the government? Yeah, buddy, yeah. You're in a plane, you hang out the plane. Don't think about this. Look at your chart and set it there. However, you know, if you ever wanted to find out where that chart came from, yeah. So the same thing here. In the digital world, you'll have a chance to deal with it. Now, all of this, to some extent, is predicated on the fact that you get your mark right there on the 0 line. Again, the chance of doing that is kind of impossible. So the question is, well, how do we plot a point where the result isn't exactly where we want it? So it could be that your mark is right here. Okay? And let's say that you're dropping from a foot. Let's say that when you make your photograph, the blur ends up to be over here. You'd like it to be here, but it's here. Is it a waste? No. What you do is you say, well, here are my inch marks. Or I'm not sure how many they are there. But you go to the middle of this, and you say, well, I would have liked it to be a foot, but it is only 8 inches. And then on the graph, instead of going to the 1 foot mark, you go to the 8 inch mark, and you plot that one there. And if your mark happens to be down here, well, in that case you say, well, how many inches below our 0 is it? And I'd like it to be at 1 foot, but no, it's at 1 foot, 12, 16 inches, let's say. You plot it here on the 16-inch dimension, or distance. And the same with all the other ones. Just because it's not at 0, it doesn't matter. All you want to know is, where did I start from, and did I get to where I want, or just a little bit less, or just a little bit more? And then you make an adjustment. And you plot that on the horizontal axis where it belongs. Not at the 1, 2, or 3 foot distance. You drop it from the drop distance that you dropped it to where the picture is. So, although I think it's a very simple, theoretically or conceptually, it's a very simple thing. The reason that this is here, or I've incorporated it into the high-speed course, is it gives you an appreciation for some of the factors that go into solving a high-speed photography problem. 99% of the time, you're dealing with stuff like this. Can I make the picture happen at the time that the event is happening? And when you have a nanosecond to work with, yeah, it's kind of tough. Or if the event lasts 10 something, and you have only 11 or something else, trying to fit the 10 into the 11, yeah, it's tough. So in a simplified way, the idea is that you experience some of that. But we're going to go a little bit further, because this is sort of intuitively, it's easy to relate to. The most difficult part is making these adjustments, and I think that I've explained it better this year than I ever have in the past. I hope so. I guess just another word of kind of warning about this. In order to secure a good trace, again, this is a moving trace, just like the moving mark on the turntable. So in order to capture or to record a significant signal associated with the moving highlight on the steel ball, you probably would like to overexpose a little bit. But again, with the digital cameras, you just look at it and you say, do I see it or not? And you just change the aperture. In a most precise world, you'd like to have that reflective point on the steel ball be infinitely small. Well, it's not going to be infinitely small, but we'll ignore that. Because if you want it to be accurate, you'd want to figure out how big the highlight is, right? Do a still shot, and then subtract it from the length of the blur, just like you did with the turntable. Take the size of the signal and subtract it from the length of the blur. I think that we're going to do okay if you don't do that, because the highlight is probably going to be quite small. Now we'll be using a nice black background, so the background shouldn't come up too much, even though some light is falling on it, and you'll be able to record the moving blur. But it pays to remember that when you're photographing moving objects, they become their own shutters, in a manner of speaking. I have I'm not going to send you there, but there's an article about something I call sensitometric velocimetry. Did I mention that last time? For example, if you have this ping pong ball over here, and it's standing still, and you measure its, let's say in film world, you measure its density or what. Let's just say you measure its digital output or something. It's 100. Okay, and you did this F8 at a 60th. Okay, and then you do another one at is that what I want? No, let's do it down here. 10. You do another one on a 30th, and now you measure it, and it turns out to be 20. And then you do the 15th, and it measures 40. Okay. That's no good. Get it with the other way around. And what am I doing here? 60. Let's say it's 100. And now you measure it at 125th. Now it's 50. It's 250. It's 25. Okay. And this ball, is it standing still when it's doing that? Yeah. I think it's standing still when it's doing that. Then, however, this ball is in motion. So here's it in motion. And you measure the density. And it turns out to be 50. The exposure time was 1 second. It doesn't matter what it is. Well, it doesn't matter as long as you have a black hole as a background. Okay? If you have a black hole as a background, and you have this moving object, and it measures a 50, in that case you can say that this thing is moving what? Well, it needs to be causing an exposure time of 125th of a second. It's moving at 125, and bear with me on this one. 125 units, and the units would be heights of this ball per second. And then if you get 25, it just means you get less and less signal because it's moving faster and faster, right? If it were moving infinitely faster, you get no signal at all. But there's a way to correlate the density here to the density here, or the value that you're talking about, digital. So this would be, this is kind of up, some of you had a friend Lembeck, no? This is along the sensitometry direction. We're using sensitometry to figure something about your subject. you know, for this you'd probably have a D-log H curve to generate for film, but it's the same idea with digital. It all goes back to that little statement that moving objects become their own shutters if they move a distance bigger than they are. So, but so far we're dealing essentially with a physics problem. Newton. He was not into biology. That was Darwin, right? So, however, there might be a connection to the natural world. And, I'm looking for something that I'm not going to find, so I'm not going to make a fool of myself digging in there. Instead, I will mention a time of the year when this particular event is happens. It has to do with the migration of the wildebeest in Africa. Can I get your attention? It has nothing to do with it. However, it's still something that happens on a regular basis in the natural world. And it has to do with trees. We know that there is a particular season of the year when around here, you know, trees drop their leaf in the fall sometimes. So that happens on a regular basis. But there are other events having to do with trees that happen on a regular basis, especially oaks, acorns. What else happens besides acorns?
Leaves change color? Leaves change color?
Leaves change color, fall thing, I guess. What else? What?
Pollen?
Pollen. You're getting. I think you're getting close. Plants are thinking ahead, right? We need more plants. How do they make more plants? Do something with seeds. Well, the acorns are close. But there's something else. And I think it's in the spring, but maybe it's in the fall, maybe it's all year long that this happens. There are these things called samaras. Anybody know what a samara is? I didn't know either, until some enlightened person told me. Any one of you seen those, when the wind blows or whatever it is, and you have these seed pods that fall from the typical oak trees? Maybe it's not oak tree. And they kind of spin around in the air? Those are samaras. Is it maple trees? Okay. So you might be interested in how those things fly. And at the beginning, I didn't know that anybody ever in history ever studied those little flying seed pods. In fact, they do. Somebody did. And what they want to know, I mean, they extrapolate all kinds of things. How is that little seed going to hit the ground? And how it hits the ground will depend, will determine how successful that seed is in surviving and reproducing another tree. Whoever thought that? I just see them fall. But so you might drive yourself to say, okay, well, I want to find out how fast those things are falling and how fast they're spinning. And maybe different kinds of trees have different kinds of seeds and they have different kinds of properties. Some might spin fast, some might spin slow, some might be irregular, and maybe Darwin, had it right. There's a reason for all of them. They succeed in various different types of earth environments. And those that are unlucky in the wrong one, they're in the wrong one. So, our objective is going to be to determine the rate at which they fall and the rate at which they spin. So, we start out with the same ruler. and the same kind of a camera set up somewhere. This time I don't think that you need to worry about a particular aim point or anything. And you know, why don't you takes a little seed that kind of looks like this, whatever. And you hold it up here and you drop it. And if you're lucky, this thing is going to spin as it comes down. Now it's possible if you look at your frame that at some point or another this little seed pod is over here. And at a later time, it'll be over here. And over here, there's the ruler. And you try to make sure, you try to arrange it in such a manner that the seed pod is close to the plane of the ruler. But approximately is okay. So if you use an exposure time that is equal to this time, in that case, at the beginning exposure, the seed will be here. At the end, it will be here. And there will be a blur between here and here, right? Just like with a steel ball, except a little bit bigger. Well, that typically is not exactly what happens because the seed pod changes position with time. So at some point, it's over here. And another point, it's over here. And then 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 it's over here, right? So now you're still talking about a blur. You'd expect this to look like, you know, a blur going that way, and then it goes that way, and it comes this way, and it goes that way, and it comes this way, and it goes that way. So the seed essentially draws out a corkscrew type shape in here. So then you know what your exposure time was, okay? This is known. You know the distance that the seed fell, okay, because it falls next to the ruler. So you say, well, it dropped so many inches in that exposure time, so the velocity is equal to change in distance divided by change in time. You know, this little relationship is about, I'd say at least 50% of all the high-speed problems that anybody solves. It has to do with how fast it's moving. In our case, it's whatever it might be. I would say, make it easy for myself. I get 1 foot. Make that, let's say, 1/4 of a second. And this is a case where you don't want a really short exposure time. Because if you get a short exposure time, well, you get a seed that looks like this in your frame. That's no good. You don't learn much from that. Oh, if the seed looks like that, yeah, that's fine. But you can't determine how fast it's moving. So you purposely want to introduce blur. And in this case, this would come out to be 4 feet per second. You can, again, in the digital world, you can determine. You make a couple of test shots and say, well, I like this speed. Now, the other thing is, I said, you know, you want to determine the rate, the rotation rate. Oh, how did I figure that one out? Well, it's an approximation. Okay. But you look at the photograph and you say, well, in order for this to be like this, the seed must have been pointed, you know, in that direction. You look at it from the top, you know, it's pointed that way. Over here, it's pointed this way. Over here, it's pointed that way again. So between here and here, how many degrees did it turn? 360. That's equal to 1 revolution, right? So you say, okay, well, once, twice, and in this case, you know, I drew the drawing maybe, you know, 3 times, or if it ends up over here, this is how many revolutions? 2.5. So you use a little logic to look at the photograph. You say, I can deduce from this turned, you know, roughly 2.5 times. And rate, again, equal to change in position, or divided by change in time. And this would be 2.5, 2.5 revolutions in, suppose again it's 1/4 of a second. And out comes, what, 4 times 2.5? 10 RPS. Okay. Typically, revolutions are not given in revolutions per second, but rather revolutions per minute. You can go with seconds, and if you want minute, you know, you just multiply times 60, so it's going 600 RPM. You could have a real fast looking, you know, fast spinner, or you have a slow spinner. It doesn't matter. You're working with whatever you have. Make sense? So that's the second part of tomorrow evening's project. And I wish I could say that I have, you know, immediately everybody can work. I don't. I have, I think, maybe 2 or 3 setups. So. I'm sorry. I think I'm done. Again, you probably want to overexpose the samara a little bit. You want to get that information. So, see you all tomorrow. Probably you want to bring a tripod. You know, I guess that would be good.
I can't let it be.